Welcome to this presentation on the 3GPP's technical specification 22.137 version 19.1.0, which focuses on the service requirements for integrated sensing and communication in 5G systems. This specification, relatively short in length, is part of release 19. I think we have 16 slides on this slide deck. It introduces a groundbreaking concept in cellular networks, and that is the integration of sensing capabilities alongside traditional communication functions. The document we're discussing today represents a significant step forward in the evolution of 5G technology. It outlines how the 5G system can be enhanced to not only facilitate communication, but also to sense and interpret the surrounding environment. This dual functionality opens up a wide range of new applications and use cases across various industries. So in this presentation, we'll explore the key aspects of 5G wireless sensing, including its operational principles, functional requirements, and performance specifications. We'll also discuss the potential impact of this technology on different sectors and how it aligns with other 3GPP initiatives in the realm of 5G and beyond. As we go through the slides, we'll delve into the technical details of how 5G wireless sensing works, the challenges it addresses, and the opportunities it creates. By the end of this presentation, you'll have a comprehensive understanding of this innovative technology and its implications for the future of wireless networks. Let's begin. 5G wireless sensing is a revolutionary technology that leverages radio frequency signals to acquire information about the characteristics of the environment and objects within it. This capability transforms the 5G system from a pure communication network into a dual-purpose communication and sensing network. At its core, 5G wireless sensing uses the same radio frequency infrastructure that facilitates communication to determine various parameters such as the distance, angle, or velocity of objects in the environment. This is achieved by analyzing the reflections, scattering, and other interactions of radio signals with objects and surfaces in the vicinity. Now, just a little bit of a sidetrack here. Now, you've probably noticed how little content I put on the slide itself, but just simple bullet points. The goal is not to crowd the slide with busy-looking text and demand you to be reading it while listening to my narratives. I'd like you to please listen to my verbal narratives without distraction and get the concepts and ideas that this specification put forth that way. Okay, back to the slide. On the middle chunk there, the key capabilities of 5G wireless sensing and what does that include? Number one is device-free object localization. Unlike traditional positioning systems that require devices to be connected to the network, 5G sensing can detect and localize objects without any attached devices. High-resolution parameter estimation. The system can estimate signal strength, delay, Doppler effect, and angle spectrum information from the scattered and reflected signals. Feature extraction. By processing these signals, the system can extract information about the location, velocity, and geometric properties of objects in the environment. These capabilities enable a wide range of potential applications across various sectors. For example, In the automotive industry, it can support assisted maneuvering and navigation, collision avoidance, and traffic management. For smart homes and buildings, it can enable intruder detection and activity monitoring. In industrial settings, it can enhance factory automation and worker safety. For public safety, it can aid in emergency response and crowd monitoring. It's important to note that while 5G wireless sensing is primarily based on 3GPP radio signals, it can also incorporate data from non-3GPP sensors like radar or cameras to enhance its capabilities. This multimodal approach allows for more robust and accurate sensing in diverse environments. So there are three different sensing operation modes that you're looking at here on the slide. 5G wireless sensing can operate in several modes, each with its own characteristics and advantages. Understanding these modes is crucial for appreciating the flexibility and power of this technology. So the first one is monostatic sensing. In this configuration, the sensing transmitter and receiver are co-located in the same entity, similar to traditional radar systems. The transmitter sends out a signal, which reflects off objects in the environment and returns to the same location. This setup is simple and doesn't require synchronization between separate transmit and receive units. However, it may have limitations in terms of coverage and the types of objects it can detect effectively. The second mode is called the bistatic sensing. This mode involves separate locations for the sensing transmitter and receiver. The transmitter sends out signals, which are then picked up by a receiver at a different location after interacting with objects in the environment. This configuration can provide better coverage and potentially more information about the sensed objects, as it captures reflections in different angles. However, it requires precise synchronization between the transmitter and receiver. The third one is called multistatic sensing. This is the most advanced configuration involving multiple transmitters and receivers. It combines the benefits of both monostatic and bistatic sensing while overcoming some of their limitations. Multistatic sensing can provide more comprehensive coverage for an area and gather more detailed information about objects from multiple perspectives. Each of these modes has its own strengths and is suited to different use cases. For example, monostatic sensing may be preferred in scenarios where simplicity and cost-effectiveness are priorities. Bistatic sensing could be advantageous in situations where you need to cover a larger area or get a different perspective on objects. Multistatic sensing, while more complex, offers the most comprehensive sensing capabilities and might be used in scenarios requiring high accuracy and reliability, such as in autonomous driving applications or complex industrial environments. The choice of sensing mode will depend on factors such as the specific application requirements, the environment in which sensing is being performed, and available network infrastructure. As 5G networks evolve, we may see hybrid approaches that dynamically switch between these modes based on the current needs and configurations or conditions. So we have this diagram here and the next one on the next slide. They're both taken out right out from the specification document. This one is depicting the monostatic sensing. So this diagram illustrates an example of monostatic sensing, which is one implementation of the 5G wireless sensing service. In this configuration, the sensing transmitter and sensing receiver are co-located within the same 3GPP system entity, similar to traditional radar systems. The 3GPP system sends out wireless sensing signals, represented here, as you can see, by solid red and blue lines. So these signals are sent out into the environment. These signals interact with objects. So the objects are represented by the red and blue circles shown here. So these signals interact with objects in the surrounding area, causing reflections and scattering, depicted by dashed red and blue lines here. The reflected and scattered signals are then received by the same 3GPP entity that transmitted them. The received signals, now termed quote-unquote 3GPP sensing data, undergo processing within the 3GPP system. The processed information then becomes quote-unquote sensing results, which are fed into the 5G wireless sensing service. These sensing results can be used by the 3GPP system itself or shared by a trusted third party, as shown in the diagram. This monostatic configuration is particularly useful for short-range sensing applications or in scenarios where space is limited. The co-location of transmitter and receiver simplifies implementation, but may have limitations in terms of coverage compared to other configurations. Now, the next picture here shows the bistatic sensing. This diagram demonstrates bistatic sensing, another implementation of the 5G wireless sensing service. In this setup, the sensing transmitter and sensing receiver are located in different parts of the 3GPP system, allowing for more flexible deployment configurations. The sensing transmitter sends out wireless sensing signals, solid red and blue lines, into the environment. These signals interact with objects. Again, the objects are represented by the red and blue circles in the surroundings, causing reflections and scattering, represented by dashed red and blue lines. A separate sensing receiver, physically distanced from the transmitter, captures these reflected and scattered signals. The received signals, termed quote-unquote 3GPP sensing data, are then processed within the 3GPP system. The processed information becomes quote-unquote sensing results, which feed into the 5G wireless sensing service. As in the monostatic configuration, these results can be used by the 3GPP system or shared with a trusted third party. This bistatic configuration offers advantages such as improved coverage and the ability to detect objects that might be hidden from a monostatic setup. This allows for more strategic placement of transmitters and receivers to optimize sensing capabilities. A little bit more information before we move on to the next topic. Now, both of these configurations demonstrate how 5G systems are evolving beyond communication to include sensing capabilities, enhancing the 5G system to a wireless communication and sensing network. The performance of these sensing operations can be affected by factors such as operating frequencies, bandwidth, and the propagation environment. Complex environment with many objects can lead to signal blockage and multiple reflections, potentially impacting sensing resolution. So we need to bear that in mind as a negative impact. While not shown in these diagrams, more advanced multi-static sensing scenarios with multiple transmitters and receivers are also possible. I don't have a diagram for that, but we have a description already we had a or already mentioned description of what multi-static sensing is. The 5G wireless sensing service is designed to work independently of positioning services. Non-3GPP sensing data from external sensors, for example, radar, cameras, Wi-Fi, etc., can be incorporated to enhance sensing results, although it is not depicted in these specific diagrams. Sensing operations and parameters can be configured for efficient use of resources such as energy and radio spectrum, which is crucial for the overall performance of the 5G network. Functional requirements. We're going to take a look at several functional requirements categories. The 3GPP specification outlines several categories of functional requirements for 5G wireless sensing. These requirements ensure that the sensing service is flexible, secure, and capable of meeting diverse use case needs. So first, let's take a look at the general requirements. The 5G system must be able to detect and track multiple objects and their environment. It should support sensing in specific target areas using designated transmitters and receivers. The system should be able to activate, configure, and deactivate sensing based on parameters like location and network conditions. Continuity of sensing service is required, especially for tracking moving objects. The system should support sensing services in roaming scenarios too, and prioritization between sensing and communication services need to be handled. How do you do prioritization? So those are implementation details. Next is the configuration and authorization functional requirements. The network must be able to configure and authorize sensing transmitters and receivers based on factors like location, time, duration, and accuracy requirements. There should be mechanisms to ensure that licensed spectrum is used only under the control of the operator providing coverage. Special provisions are made for public safety and V2X networks. V2X means vehicle to everything networks to allow sensing in out of coverage or partial coverage scenarios. Next one is functional requirements for network exposure. The network should provide secure means to report sensing results to authorized third parties. It should allow trusted third parties to request sensing services with specific parameters and receive corresponding results. The system may expose information about service availability and quality for specific areas and times. Next is security and privacy. What are the functional requirements? The 5G system must support encryption, integrity protection, and privacy of sensing data and results. Mechanisms should be in place to protect identifiable information from eavesdropping. The system should limit exposure of sensing results only to authorized parties. There should be support for appropriate sensing KPIs in situations where consent can and cannot be obtained. Next one is charging. The 5G system should support charging for sensing services considering factors like sensing KPIs and duration. So these requirements ensure that 5G wireless sensing can be deployed safely, securely, and effectively across a wide range of scenarios where respecting privacy concerns and regulatory requirements are paramount. They also provide the flexibility needed to adapt the sensing service to different use cases and business models. Now let's take a look at the performance requirements. The 3GPP specification defines a set of KPIs. for 5G wireless sensing, which are crucial for ensuring that the sensing service meets the needs of various applications. These KPIs include accuracy of positioning estimate. This measures how close the sensed position is to the true position of an object in both horizontal and vertical dimensions. Accuracy of velocity estimate. This indicates how precisely the system can determine an object's speed and direction. Confidence level. This represents the percentage of measurements expected to fall within the specified accuracy range. Sensing resolution. This describes the minimum difference in measured magnitudes, for example, range, velocity, etc., that allows the system to distinguish between different objects. Missed detection probability. The likelihood of failing to detect a present object. False alarm probability. The chance of incorrectly detecting an object that isn't actually present. Max sensing service latency. The time between an event triggering a sensing operation and the availability of the result. Refreshing rate. How frequently the system updates its sensing results. This specification provides a detailed table of performance requirements for different sensing scenarios. These scenarios, by and large, are categorized into 3 areas: object detection and tracking, environment monitoring, and motion monitoring. Again, if you need to implement any kind of applications belonging to any of these categories, you need to check the specification for the actual KPI numbers. So those are not in this presentation because those are for implementation. So you need to check for the spec for those. For each scenario mentioned here, specific values are provided for the relevant KPIs. For example, in one scenario on the spec, it mentioned indoor-outdoor detection of humans or UAVs, unmanned aerial vehicles. The system should achieve, this is just an example I provide here, but you do need to check back on the spec to verify. So on this one scenario, I was just saying, describing an indoor-outdoor detection of humans or UAVs, the system should achieve about 10 meters horizontally, and the vertical accuracy needs to be about 95% confidence level, 95% confidence. The 10 meters range resolution and a 1-second refresh rate. In another scenario, as an example, for indoor-outdoor detection and tracking of humans, animals, UAVs, AGVs, or vehicles. These are all aerial vehicles, unmanned vehicles, or just vehicles. The requirements are more stringent. It's about 0.5 meters accuracy and 99% confidence for public safety applications. As you may imagine, public safety is important. We're dealing with human life, so 99% confidence level and latency between 100 to 5,000 milliseconds, depending on the specific use case. These performance requirements are indeed crucial for ensuring that 5G wireless sensing can meet the needs of diverse applications. They provide a benchmark for system designers and operators to aim for when implementing sensing capabilities in 5G networks. It's worth noting that these requirements may evolve as the technology matures and new use cases emerge. So there's certainly flexibility there, and we have new use cases popping up almost on a monthly basis, if not even sometimes weekly basis. So we need to keep up to date on all of these specifications. Excuse me. The introduction of sensing capabilities in 5G networks brings new challenges related to security and privacy. These aspects are crucial to address to ensure the responsible and ethical deployment of 5G wireless sensing technology. There are confidentiality challenges. The 5G system must protect sensing data from unauthorized access, interception, and eavesdropping. We talked about this a little bit earlier. This is particularly important because sensing data can reveal sensitive information about the environment and individuals within it. The specification requires that the 5G system support encryption and integrity protection for all sensing data, including 3GPP sensing data, non-3GPP sensing data, and derived sensing results. The privacy considerations is one of the most significant privacy implications of 5G wireless sensing in its ability to track people and objects in the environment, including those not carrying UEs. You don't have to carry a device for you to be tracked. That's the bottom line, and it could be scary. This capability raises important ethical questions and necessitates robust privacy protections. The specification addresses this by requiring mechanisms to protect identifiable information derived from sensing data from eavesdropping, limiting the exposure of sensing results only to authorized, trusted third parties, supporting appropriate sensing KPIs for situations where consent can be obtained or it cannot be obtained. In terms of regulatory compliance, the specification emphasizes the need for 5G wireless sensing to comply with regulatory requirements, and this includes ensuring that the use of licensed spectrum for sensing is only done under the control of the operator providing coverage. We did mention this also before. Providing mechanisms to configure and authorize sensing operations based on factors like location, time, and sensing area. Allowing for the linking of sensing results with 3GPP subscriber identity only with user consent and in accordance with regulatory requirements. It is important to note that these security and privacy aspects will likely evolve as the technology is deployed and as regulatory frameworks adapt to the capabilities of 5G wireless sensing. Network operators and service providers will need to stay vigilant and adapt their practices to ensure ongoing compliance and protection of user privacy. Furthermore, the implementation of these security and privacy measures should be designed in a way that doesn't significantly impact the performance of the sensing service. This balance between security, privacy, and performance will be a key challenge in the deployment of 5G wireless sensing technology. Use cases and applications. 5G wireless sensing opens up a wide variety of potential use cases across various sectors. Let's explore some of the key application areas. Smart cities and urban planning. 5G sensing can provide valuable data for urban planners and city managers alike. It can be used for things like traffic monitoring and management, helping to optimize traffic flow and reduce congestion. Crowd monitoring in public spaces, aiding in public safety and event management. Environmental monitoring, including air quality sensing and flood detection. Smart parking systems, helping drivers find available parking spots more efficiently. Ain't that nice? All these features from wireless sensing. Automotive and transportation. In the transportation sector, 5G sensing can enhance safety and efficiency. Like vehicle to everything, V2X, this is a protocol. V2X communications, vehicle to everything communications can be augmented with sensing data to improve collision avoidance systems. Traffic signal control can be optimized based on real-time traffic sensing. Autonomous vehicles can use network-based sensing to complement their onboard sensors. Railway systems can use sensing for track monitoring and train detection. Next is the Industrial IoT and Industry 4.0. In industrial settings, 5G sensing can support things like asset tracking and inventory management in warehouses and factories, worker safety monitoring, detecting potential hazards or unauthorized access to dangerous areas, predictive maintenance by sensing unusual vibrations or movements in machinery, quality control in production lines, detecting defects or anomalies. Healthcare and well-being. 5G sensing has potential applications in healthcare, like fall detection and mobility monitoring for elderly care, sleep monitoring and analysis, contactless vital sign monitoring, like for heart rate, respiratory or respiration rate, etc. Activity recognition for fitness tracking and rehabilitation. How about public safety and emergency services? The last item. 5G sensing can enhance public safety operations for sure, like intruder detection in secure areas, search and rescue operations potentially detecting people in disaster areas, fire detection and monitoring in buildings or forests, crowd management during large events or emergencies. These use cases demonstrate the versatility of 5G wireless sensing. As the technology matures and is integrated with other emerging technologies like AI/ML and edge computing, we can expect to see even more innovative applications emerge. The key to unlocking the full potential of 5G sensing will be in developing robust, secure, and privacy-preserving systems that can reliably deliver these services at scale. So how do we integrate 5G wireless sensing into other services, 5G services? The integration of wireless sensing capabilities into 5G networks creates interesting synergies and challenges at the same time when considered along existing 5G services. Let's explore how sensing interacts with other aspects of the 5G ecosystem. Its relationship with positioning services. That is 5G wireless sensing, its relationship with positioning services. While 5G wireless sensing and positioning services share some similarities, they are distinct capabilities. They're not the same. Positioning typically focuses on locating UEs connected to the network, while sensing can detect and track objects without attached devices. The 3GPP specification states that wireless sensing is expected to work independently of positioning services. However, there may be opportunities for these services to complement each other. For example, sensing could provide additional context to enhance the accuracy of positioning services, especially in challenging environments like indoor spaces. Synergies with communication services. 5G wireless sensing leverages the same radio frequency infrastructure used for communication, creating potential synergies. The high bandwidth and low latency of 5G networks can support real-time sensing applications. Massive MIMO and beamforming technologies, crucial for 5G communication, also enable high-resolution sensing capabilities. Network slicing could be used to allocate resources dynamically between sensing and communication services based on current demands. However, there are also challenges to consider. The network needs to balance resources between sensing and communication functions. Interference management between or becomes more complex. You can imagine it's more complex when the same spectrum is used for both sensing and communication. So those challenges need to be overcome. There needs to be on the implementation level. We need some clever solutions. Next is impact on network planning and optimization. Introducing sensing capabilities affects how 5G networks are planned and optimized. Network densification. Already a trend for improving 5G coverage and capacity, also benefits sensing by providing more diverse perspectives for object detection and tracking. The placement of base stations may need to consider both communication coverage and sensing coverage requirements. New optimization algorithms may be needed to dynamically allocate network resources between sensing and communication functions. The introduction of sensing may require updates to self-organizing network, SON in short. SON is the acronym for self-organizing network. So the introduction of sensing probably requires quite a bit of update to self-organizing networks capabilities to automatically configure and optimize the network for both functions. So that's a bit of work right there to do the updates for all those SON networks, self-organizing networks. Again, as 5G networks evolve to incorporate sensing capabilities, we can expect to see new tools and methodologies developed for integrated network planning and optimization. This could lead to more flexible and efficient use of network resources, ultimately benefiting both sensing and communication services. The integration of sensing with existing 5G services represents both an opportunity and a challenge for network operators and equipment vendors. Successfully navigating this integration will be key to realizing the full potential of 5G wireless sensing technology. The last point I want to mention before we move on to the next topic is what is the impact on network planning and optimization? I thought we sort of talked about this before. Yeah, I think we did talk about this already. This is a duplicate slide. Sorry about that. I'm going to move on to future directions and challenges. As we look to the future of 5G wireless sensing and beyond, several key directions and challenges emerge. Evolution towards 6G. So I have been working with 6G technology for at least a few years, and so there's an army of people already looking towards 6G. 5G wireless sensing is laying the groundwork for even more advanced capabilities in future network generations. 6G networks are expected to further blur the lines between sensing and communication, potentially treating them as a unified service. High frequency bands in 6G, for example, sub-terahertz and terahertz, could enable even higher resolution sensing, potentially allowing for molecular level sensing and imaging. Those are very cool technologies. The concept of quote-unquote Internet of Senses in 6G envisions a network that can replicate human senses, building upon the foundation laid by 5G sensing. Research and standardization needs. Several areas require further research and standardization efforts. One is advanced signaling processing techniques. We need that to improve sensing accuracy and resolution, especially in complex multipath environments. Certainly, integration of AI/ML algorithms for real-time processing and interpretation of sensing data. Standardization of interfaces between sensing systems and various applications to ensure interoperability. Development of testing and validation methodologies for sensing performance considering diverse environmental conditions. So those are all areas that need further studies and work. Next is an important topic, ethical and societal implications. The widespread deployment of sensing capabilities raises important ethical questions. Privacy concerns. How do we balance the benefits of sensing with individuals' right to privacy in public spaces? Data ownership and control. Who owns the data generated by sensing networks? And how should access be regulated? Potential for misuse. How can we prevent the use of sensing capabilities for surveillance or other potentially harmful purposes? Digital divide. Could the deployment of advanced sensing create new forms of inequity between areas with and without these capabilities? Are we widening the digital divide? So all those are questions unanswered, and people are working on them. Addressing these challenges will require collaboration between technologists, policymakers, ethicists, and the public. As 5G wireless sensing evolves and paves the way for 6G, it will be crucial to consider not just what is technically possible, but what is socially responsible and beneficial for society as a whole. As we conclude this presentation on 3GPP TS22.137 and 5G wireless sensing, let's recap the key points and consider the broader implications of this technology. So let me give you a summary of 5G wireless sensing capabilities. 5G wireless sensing represents paradigm shift in how we utilize mobile network infrastructure. By leveraging the same radio signals used for communication, 5G networks can now do the following. Detect and track objects without requiring them to carry devices. Monitor environmental conditions with high accuracy. Enable a wide range of applications across industries from smart cities to healthcare. This dual use of network infrastructure for both communication and sensing offers unprecedented opportunities for innovation and efficiency. Importance in the evolution of mobile networks. The introduction of sensing capabilities marks a significant milestone in the evolution of mobile networks. It expands the role of mobile networks from pure communication platforms to intelligent, context-aware systems that can interact with their environment. It opens up new revenue streams for network operators, potentially offsetting the high costs of 5G deployment. It lays the foundation for even more advanced capabilities in future network generations, bridging the gap between the digital and physical worlds. Last slide, call to action for stakeholders. For this technology to reach its full potential, various stakeholders need to take action. Network operators should start planning for the integration of sensing capabilities in their 5G deployments and consider how it might affect their business models. Equipment vendors need to develop hardware and software solutions that can efficiently support both communication and sensing functions. Application developers should explore how 5G sensing can enable new use cases or enhance existing ones in their domains. Policymakers and regulators must work on frameworks that balance innovation with privacy protection and ethical use of sensing technology. Researchers should continue to push the boundaries of what's possible with wireless sensing, addressing challenges in areas like signal processing, AI/ML integration, and energy efficiency. In conclusion, 5G wireless sensing, as outlined here in the 3GPP-TS 22.137 spec, represents an exciting new frontier in mobile network technology. It has the potential to transform how we interact with our environment and enable a new generation of intelligent, context-aware applications. However, realizing this potential will require careful consideration of technical, ethical, and societal factors. As we move forward, it will be crucial to ensure that the development and deployment of this technology aligns with broader societal goals and values. Thank you for your attention. See you in the next 3GPP spec. Goodbye.